Okay, class, in this lesson we're going to be analyzing graphs of polynomials. We're going to review, really, how we graph a polynomial function. We're going to learn about this thing called the location principle. We're going to define turning points and understand its relationships to polynomials. And we're going to identify whether we have an even or odd polynomial function. Okay, first off, steps to graph a polynomial. We've done this. First of all, we want to graph the x-intercepts. We want to factor and find all the zeros. We want to look at the end behavior to figure out how it behaves at negative infinity, positive infinity of x. And then we would like to plot any convenient points. And what I mean by convenient points are points, maybe the x-intercept where x is equal to 0, or maybe some other points that are close by to the x-intercepts that we've already found. So here's an example. X minus 2, x plus 3 squared times 1/4. My zeros are 2 and 3 respectively. And my behaviors at each one of them, it crosses at the 2 because it's the power is to the first power, which is an odd number. Odd degree factor, so it's crossing. Even degree factor, it's going to be touching. The way I remember it, this is a little trick. Y is equal to x to the first power. If we were to graph this out, we would have this graph right here. It crosses. We have y is equal to x squared. If we were to graph this one out at the 0 right here, it touches. So that's an easy way to me to remember this. When it's odd, the exponent's odd, it crosses. When the exponent is even, it just touches, just like a parabola. Okay, I plot those out. Think about the end behavior. My end behavior is determined by the power, the leading the degree of the polynomial. This is x to the first times x squared. So I'm going to get an x to the third term. My degree is going to be 3. Leading coefficient's positive. So it's going to behave like a positive slope line. It's going to start out over here and rise up here. So I put those arrows in. I plotted out another point, plugged in 0 into my equation. 0 here gets me negative 9/2 over here. Then I connect all those points out. So that's how I graph, and we've gone through this. Okay, let's look at the location principle next. Location principle says this. Starts off with this kind of definition. If I have a function f of a, if it's negative, and also if I have f of b, which is positive, and here's the picture of it. F of a, negative, f of b, positive, greater than 0. This is my, I should label this, this is my x-axis. Positive up here, negative down here. My polynomial must go through here. It must somehow go through here up to this point. The only way to get from one point to the other point is by crossing through this x-axis here. When it crosses through the x-axis, it's one of our zeros. So we know that it crosses through at least once. Maybe it goes down and comes back up again, but we're going to get at least 1 0 if between a and b it goes from, say, a negative value to a positive value here. How do we apply this? Okay, let's look at this polynomial here. It's kind of a mess. We can't factor it. We got to list out all the different factors of 6 for our numerator. We got to list out all the different factors of this leading coefficient for our denominator. We think of all the different combinations and we list them all out here. There's quite a few. Where do we start? Well, if we're given a table, in this case, let's assume we have a table, and we see that right at the x is equal to 1 to x is equal to 2, it goes from negative 12 to 28. It crosses over from negative territory to positive territory. The crossover happens between x is equal to 1 and x is equal to 2. So we know that the 0 must be somewhere between 1 and 2. So immediately we can rule out a bunch of these as things we need to look at, and we could just bother to look at 3/2 because that's between 1 and 2. Okay, if we were to look at this, then we have run through the synthetic division here. We get a remainder of 0, which is good. It says that 3/2 is one of our zeros. X minus 3/2 is one of our factors. So we have our factor here. We could create our other part of our quotient factor here. Now we're going to factor this. This is a quadratic, so it's kind of nice. Factor out the 2 that's common in the 6, 14, and 4. So once we factor out the 2, we're left with this, and we could actually factor this. This is 3x plus 1 times x plus 2. Okay. This leads us to our factors, or our zeros, of 3/2 from here, negative 1/3 from here, and negative 2 from here as well. Okay? So that's how we can apply the location principle. It helps us to narrow down our search for our possible root if we were kind of given some other information. Okay, turning points. Let's define a turning point. A turning point is any sort of local minimum, local maximum here. We call this a local maximum here because even though it's not the highest point, this graph keeps going up and up and up. So it's not, this is the higher value, a greater value than this, but we call this a local maximum because in this little region here, this is the maximum value. Just like in this little region over here, this is the minimum value. We could also consider a turning point as where the function goes from increasing to decreasing. So the green region shows increasing portions, the yellow shows decreasing. So between the green and the yellow, we have a turning point as well as another turning point down here. Okay, so that's the definition of turning points. We have some key properties of these turning points. In a polynomial, if the polynomial is of degree n, there's at most n minus 1 turning points. What this means is the following. X to the 5th power. At most, it will have 4 turning points. It will not turn 6 times. It won't even turn 5 times. Here's some other really nice examples. I always like to look at simple examples which we already know. X squared. According to the theorem, it should not have more than 1 turning point, and indeed it does. It only has 1 turning point. Let's look at y is equal x to the 1st power. According to the property here, it should have 0 turning points, and in fact it does. It's just a line, no turning points at all. So it does fit even these simple cases here. Now I could do the following. Say I had, this is my polynomial, and I count 1, 2, 3, 4, 5, 6 turning points. 6 turning points means that this polynomial is at least of degree 7. It could be of degree 9, it could be of degree 11, but at a minimum it's degree 5. We know that this polynomial here with this kind of graph behavior cannot be 5th order. The end behavior here would suggest an odd degree, but the turning points give us even more information, and it says that it must be greater than 6. It must be at least 7 or beyond in odd increments. Okay. Another property. A polynomial with n non-repeated zeros. And this is what I mean by non-repeated. Remember when we have, say, a factor at x minus a, if it's to the 1st power, it's not repeating. So in this case, it means that all the 0 behaviors are crossing type of behaviors. If that's the case, then the only way to get these zeros here is if it goes up, down, up, down, up, down, which creates, in this case, exactly 5 turning points. So the theorem says if there are n non-repeating zeros, there has to be exactly n minus 1 turning points. Okay, last idea of the day, even and odd functions. We haven't really talked about this before, so we're going to define what an even function is and an odd function. This is the definition. F of negative x is equal to f of x. If that's the case, it's even, but that's kind of a confusing looking sentence here. What does it mean? Okay, let's start with, actually just ignore this piece over here. Let's start with f of a. Let's say right there. If this is f of a, then f of negative a, according to this, f of negative a is the same as f of a. Means it's the same height. The y values are exactly the same. So they're opposite sides of the graph, in respect to the x-axis, but they're the same height. It's a reflection. This is a reflected point across here. Now, I could have these other points here, same thing. This is a reflection across the y-axis. Same with these 2 points. Same with these 2 points. Same with this point that sits on the axis. We can connect this all together. This will give us an even function, and the visual quality of it is that we can see from the graph that it's symmetrical over the y-axis. It has line symmetry is what we would call it. An odd function is slightly different, very, very subtle difference. The difference is right here, the negative sign. Everything else is the same. F of negative x is the opposite of f of x. What does this mean? Again, let's ignore this piece right here for now. Let's just look at f of a. What it's saying is the following. If f of a is up here, then at negative a, instead of it being over here, like an even function, this would be f of negative a if it were exactly the same. Instead, it's the opposite. Instead of it being up here, it's down here. So you could actually imagine it's actually what's going on is I'm taking this, I'm reflecting it across the y-axis as if it were even, but I'm reflecting it again across the x-axis to get it down here. These 2 pairs are related pairs. This here, this here. These 2 points. This point right at, oops, let me go back. This point right at the origin, and then these 2 points. If I connect this all together, I get a graph like this, and the key property is that it's going to be a 180-degree rotation around the origin, and also I have a 0 at the origin. Okay, so visually we can look at each one of these and determine whether they're even, whether it's odd, or whether it's neither, because sometimes it might be neither of them. In this case here, we have an odd function. If I were to, do a 180-degree rotation, it would land exactly on itself. This one over here, neither. If I were to flip this upside down, both of these arrows would be down here, so it's obviously not an odd. And at the same time, if I were to fold it in half, this point over here would go over there, so that doesn't make sense either. And I have another way to look at it is I have these 2 turning points on this side. If I were to reflect it on the other side, I only have 1 turning point on this side, so it's not symmetrical by line symmetry or by rotational symmetry. Next one here, this one is even. I could fold it in half. Right up along this line, it would fall onto itself. This one over here, this is odd. Again, imagine we rotated it by 180 degrees. It would land exactly on itself. And it has a 0 right at the origin. Okay, we have another even function here. We could fold it in half. You notice for even functions, it doesn't matter. This point here, it doesn't have to be at the origin. And then this last one is neither. You can see that at the origin, We don't have a point, so it's not odd. And we see that if we folded this, it would just not, it's not even. We can't fold it onto itself. Okay, so visually we could see by its symmetry whether it's even, whether it's odd, whether it's neither of them. Let's look at an algebraic method as well. Okay, here's a function. What is it? Is it even? Is it odd? This is our test. We're going to plug into f of x, or we're going to plug into the function negative x. So I'm going to plug that into x to the third. I'm going to plug it into my 7x. Now, negative x to the third is going to be x to the negative x to the third. And now look at this. Look at what I have. If I were to do some simplification here, the green portion's exactly the same, but you see this negative sign in front of it. So it's negative of the function, and so we call this an odd degree. Let's do the same. Let's do it for g of x. We're going to test that out same way. Plug into itself negative x. When I do this, look what happens. Negative x raised to the fourth power is just going to be x to the fourth. Negative x raised to the second power is just x squared. The negatives really don't have an effect because once I raise it to the fourth power, it just disappears. So in this case, we see that the functions are exactly the same. It started out to be this. I applied a negative x to it. Same thing. So in this case, we say it's even. Last case, h of x. Same idea. This is the same test methodology. Plug in negative x in here. Now when I do this, this is not equal to h of x. It's not equal to the opposite of h of x as well. So we say this is neither. So that's our test. That's our method. So go ahead, try out these problems. There's a set of problems. I'll show you the answer in 4, 3, 2, 1. Okay, have a good day, everybody.